Now we're going to take a look at the free response of a coupled RC circuit. So here, the switch in this combined circuit where we have two capacitors and two resistive elements has been closed for a long time, and all of a sudden we're going to open that switch, and we're going to determine how the potential across C1 changes as a function of time. Now, this is meant to illustrate the importance of determining the determining the differential equation to inform how the system is going to respond. In this case, it's a little bit different than we've seen before. We have two of the same type of energy storage elements, but they are distinct energy storage elements because we can't combine the capacitors in parallel or in series because C1 and C2 are both separated by this resistance R1. Okay, so we're going to have to take a slightly different approach, but it is a very familiar approach. Remember that elements are just circuit elements, and we can treat them the same way that we would resistive elements. We just have different current to voltage relationships for those elements. All right, so the system that we want to analyze looks like this. Right, so we want to develop a differential equation that's going to describe how the voltage across this capacitor C1 changes with time. To do this, we're going to have to, since we're looking for voltage, we're going to apply the node voltage method. But we need to look at the nodes that we're interested in analyzing. So in this case, we definitely need this node right here, because that's the one of interest. We also have this bottom node, which we're going to call our ground reference node. And we have this node right here that joins C2, R2, and R1 together. So now, if we're going to perform a node balance, we actually have two nodes that we're going to need to perform the balance on. All right, so one is this V out node, and this one right here I'm going to call V1. All right. So performing our node balance for the V1, or excuse me, for this node, the output node, I'm going to look at the paths that current can leave from that node. And for the V out node, this one right here, current can pass through the capacitor after that switch opens, or through the resistor R1. All right, so the sum of the current through the capacitor plus the resistor has to sum to 0. Now I'm going to substitute in my current to voltage relationships. All right, for my capacitor, I know that it is the value of the capacitance times the derivative with respect to time of the potential difference across that capacitor. So that is going to be my V out node minus 0. For the resistor, R1, I know that the current to voltage relationship is the potential difference divided by the resistance. So here, we're going to assume, again, like we've always done with the node voltage method, that the node that we're analyzing is at a higher potential than the direction towards which it's going, or to which it's connected. So the current is going to leave the node, so that means that V out must be larger than V1, and the difference is going to be divided by the value of R1. And all of that must sum to 0. Alright, so taking this derivative and rearranging things a bit, I wind up with an equation that tells me that R1 C1 times the first derivative of the output voltage with respect to time plus V out has to be equal to V1. You say, wait a minute, that's a first-order differential equation. Well, of course it is. That's what we would expect with one energy storage element here and a resistive element leading to V1. But what we have is a case of coupled first-order systems. So over here, since we have a capacitor connected to V1, to my V1 node, we're also going to get a first-order equation. But that first-order equation is going to depend upon the V out output voltage. So we have coupled first-order systems, or first-order equations, because V out depends on V1, and V1 is going to depend upon V out. So let's develop that equation for the V1 node. All right. from V1, we can have current that leads through resistor R2 down to ground, so IR2. We could have current leave through capacitor 2, or we could have current leave, actually let's do resistor 1 here, capacitor 2, or we could have current leave through resistor 2. Alright, so we have 3 paths for current. All of those have to sum to 0. Alright, for the current through R1, we're going to use, again, how we've typically done it for node voltage method, so V1 minus Vout node voltage divided by the resistance R1. For capacitor 2, since that's connected to ground, or to our low side, or 0 voltage reference, the current to voltage relationship is C2 dV1 dt, because we're analyzing the potential at that node V1. Alright, and finally for resistor 2, the voltage is V1 minus 0 divided by the resistance R2. All of that has to sum to 0. Alright, so now I can do some more rearranging and multiplying through by terms, and when I perform my algebra, I wind up with a first order differential equation that looks like this: R1, R2, C2 times the first derivative of V1 with respect to time plus R1, R2 times V1 is equal to R2 V out. Alright, so again, we have 2 first order differential equations, and they're coupled to each other because the output voltage depends upon V1 and V1 depends upon V out. Alright, what we'd like to do is to come up with a single second order differential equation that will describe the system. So what I'm going to do is I'm going to take my result for V1, since this is in terms of V1, and substitute it back into this differential equation right here. Yuck. Alright, well, let's do that. Alright, so first of all, I recognize that I'm going to have to substitute not only V1, but the derivative of V1 with respect to time back into this equation. So the first thing I'm going to do is take dV1, I'm going to take the derivative of this equation right here. So the derivative with respect to time of this result, since R1 and C1 are both constants, I'll get a second order derivative here. R1 C1 d squared V out dt squared plus, dV out dt. Alright. This becomes messy, it becomes an algebra nightmare, but we can take care of it, we can handle it. Alright, so my first term here is substituting the V out relationship that I got right here back into this equation. What I'm trying to do is eliminate my V1 variable and get everything in terms of V out. Alright, so doing so gives me R1, R2, C2 times all of this stuff. R1, C1, the second derivative of the output voltage with respect to time, plus dV out dt. Alright, plus R1, R2 combination, plus V1, which is this equation right here, and all of that is equal to R2 V out. Okay. Now, what I'm going to do is gather like terms, multiply things through, and try to get this into the general second order form. And when I go through my algebra, I should wind up with my second order differential equation and my second order term being multiplied by R1 squared R2 C1 C2 times the second order derivative of the output voltage. Alright, what's in front of my first order terms right here will be R1 R2 C2 plus R1, R2 times R1, C1. So that's those terms right there, times the first order derivative. And my first order term will be comprised of R1 plus R2, and I have an R2 term over here, so if I bring that back over to the left-hand side of the equation, the positive R2 term and the negative R2 term are going to cancel each other out because they're on opposite sides of the equation. So the 0th order term is just going to be R1 times V out. And that is going to now be equal to 0 because I brought this back over. So as messy as it looks, I have a second order homogeneous differential equation with constant coefficients. All of these terms right here comprise the inertia of the system. All of these terms right here comprise the damping of the system, and R1 is the stiffness of the system. Okay, so it's pretty messy, but we were able to come up with a second order differential equation that's going to describe this coupled system of two first order systems joined together. Okay, so we know the value of M and C and K, and the other thing that we need to do is we need to plug in values, and when we plug in our values, we should find well, maybe that it's not going to work. Okay, now we find that we have our two coupled first order differential equations, and we combine those together. And I hope this thing is going to change now. Okay, and we combine them into one second order differential equation. It's a homogeneous linear differential equation, and we can use our node balances to determine the initial conditions. We'll go ahead and do that, and we also need to establish the order of the system. So if we plug in values to our damping ratio, if we solve for values of M and C and K, we find that M is equal to 1064.8, C is equal to 7524, and K is equal to 2200. Alright, so plugging those into my differential equation, into my definition for the damping ratio, I find that if I take C over 2 square root of Km, if I use those values, I wind up with 2.4579 for the damping ratio, which means the system is overdamped. Okay, and I know the form of the overdamped solution. I can also find squiggle and omega n. The product of those two is going to be 3.533 radians per second. And I can find my eigenvalues to be, if I use the eigenvalue formula, to be negative 0.3056 and negative 6.76. Okay, now I need to, now that I have those, I know that the general solution, since it's overdamped, that the voltage across capacitor C1 as a function of time is going to be given by AE to the first eigenvalue, negative 0.3056 times time, plus some unknown constant b times e to the negative 6.76t. And I have to turn my attention now to defining the values of a and b based on the initial conditions. Alright, so to define the initial conditions, I'm going to go back to my node my node balances and what the system looks like at time equals 0. Alright, so before time is equal to 0, I have my 50 volt source connected to capacitor C1, R2, C2, and R2. Alright, so before time is equal to 0, using the properties of capacitors in the DC steady state, if they've been operating for a long period of time, I know that capacitors act like open circuits because the electric field has become fully established and no current is allowed to pass through the elements. Resistors stay the same. Alright, so in this case, right before the switch is opened, sorry, that's R1 right there, R1. The two capacitors act like open circuits, so I know that across this capacitor C1 at time 0 right before the switch opens has to be equal to the 50 volts of potential that's being supplied to it. I also know from the property of capacitors that as soon as that switch opens, the potential across the capacitor cannot change instantaneously. So since the potential can't change instantaneously, that means right after time is equal to 0, the capacitor, right after that switch opens, the potential across the capacitor still has to be 50 volts. Okay, now we need to determine the derivative initial condition, or the rate of change of the potential across the capacitor. Alright, so what we're going to do is we're going to return to our node balance for the for this Vout node right here. And we saw that the node balance, according to Kirchhoff's current law, was given in this form right here. Alright, so we apply Kirchhoff's current law, but we also see that we can derive our first order equation based off of Kirchhoff's current law. Alright, so we said that right after this switch opens, the current through capacitor 1 plus the current through resistor 1 had to sum to 0. Alright. Then from that we developed our first order differential equation, which said that R1C1 times dVout dt plus Vout had to be equal to V1. Alright. This has to apply at time is equal to 0, the instant right after the switch opens. So we can also say that R1C1 dVout dt, right after that switch is opened at time 0, this has to be true. Okay, and we just said that we know that the output voltage at time at 0 has to be equal to 50 volts. Alright, so we can rewrite this as R1C1 dVout dt at time 0 plus 50 volts has to be equal to V1 at time 0. Alright, so our attention now has to turn to what is the potential across capacitor 2, or at the V1 node at time is equal to 0. Well, we can determine that, again, because we know how capacitors behave. If they've been operating in the DC steady state, we know that the potential across the capacitor the electric field is going to be fully established, so the potential across the capacitor is going to be, no current is going to flow through the capacitor. So we can determine the potential across the capacitor. In this case, since our circuit looks basically like two resistors in series with each other, we can use the voltage divider equation to determine the potential that's developed across C2, which is also our V1 node, right before the switch is opened. And because of the properties of capacitors, we know that the potential across that capacitor can't change instantly. So as soon as the switch is open, we're going to have that same potential across it. So just before the switch opens, the potential across this capacitor will be 50 volts times the value of R2 over R1 plus R2. Okay, and I know that since the potential across the capacitor C2 can't change instantaneously, that means that VC2 right after the switch opens is equal to V1 at time 0. And that's going to give me the value if I evaluate that. Alright, so, and unfortunately I have not evaluated that, so I'll leave that to you to evaluate. Alright, so that tells me that if I can find that value, that the derivative initial condition is going to be equal to V1 at time 0 minus 50 divided by the value of R1C1. And this is something that I have evaluated, and when you plug in your R and C values and the value that you get for the the output voltage at V1 right before or right after that switch opens, I get a value of negative 227.27. Okay, so now I know my initial condition as well as my derivative initial condition, and this should be in units of volts per second. Since I know those values, I can use my general solution approach and plug in those values to come up with my unknown constants A and B. And when you do that, we should wind up with a result that looks like this. All right, we have our two coefficients now that were determined based on our initial conditions. So we know that the potential across the capacitor 1, or our output voltage, is given by this function right here. And what we see is that the potential initially starts at 50 volts. It rapidly decreases, and then as things start to equilibrate, that rate slows down. So this the second term dominates initially to contribute to that decrease, and then things slow down and the energy dissipation slows down until it approaches 0. And this is a behavior that we should expect because this is, first of all, a free response case. So all of the energy is going to dissipate, so the system should tend towards a value of 0. And since it's an overdamped system, and an extremely overdamped system at that, there's going to be a slow approach to the 0 steady state condition.